now I think we are
Awesome.
perfect.
Very good.
And thanks again, everybody, for being here today for the AI for Science seminar. Today, we're going to hear from Ricardo Vinuesa, who is an associate professor in engineering mechanics at KTH. He is also lead faculty at the KTH Climate Action Center. So Ricardo studied mechanical engineering at the Polytechnic University of Valencia, and he received his PhD in mechanical and aerospace engineering from the Illinois Institute of Technology in Chicago. So Ricardo has received many awards over his career, including an ERC Consolidator Grant, the Göran Gustafsson Award for Young Researchers, the CERS Young Researcher Award, and he also leads several large Horizon Europe projects. And he's a member of the Young Academy of Science of Spain. So his research combines numerical simulations and data-driven methods to understand, control, and predict complex, well-bounded turbulent flows, such as the boundary layers developing around wings and urban environments. And we're very happy that he accepted our invitation to come here for the seminar. So now the floor is yours, Ricardo.
Thank you very much for the introduction, also for the invitation. It's a great pleasure to be here. I'm going to be talking about turbulent flows and how to use deep learning to try to explain and understand some of the physics and also to control turbulent flows. And I know that the audience is a bit mixed, so I will show a little video at the beginning to try to illustrate what these flows look like and the type of physics that we want to be understanding. This is funded by the ERC, the European Research Council. So I'd like to start by acknowledging my many collaborators. Let's see if we can make it work. Here we go. Without whom this would not be possible. So this is really a big research group and a big collaboration with international top people who really help and contribute a lot to this project, and many others that are not even listed here. So this is really thanks to everybody involved. Let me start by showing a little video. This is I've been having meetings the whole day with students and postdocs and faculty, and the question was, how do I generate the data? So I just wanted to show a little video to illustrate how we generate the data. This is a high fidelity simulation. It's almost DNS resolution. This is a spectral code using adaptive mesh refinement. What you can see here is a wing. A wing section. This is a NACA 0012 profile. We consider different angles of attack, so different inclinations of the wing. And the interesting thing here is this wing tip. You can see that the wing is finite and there is a rounded edge at the end of the wing tip. This produces, on the one hand, a turbulent flow on both sides. So you have these two turbulent boundary layers that you can see are chaotic. This is what characterizes turbulence around well-bounded turbulence around these wings. The flow is really chaotic. And you can also see that at the end of the wing, you have a wingtip vortex. So the flow basically rolls around this wingtip and pushes the wake down. So the flow after the wing is being pushed down in such a way that the ability of the wing to extract lift from the flow is diminished, and that adds an additional contribution to the drag, which is the lift-induced component. I don't want to get too deep into the aerodynamics or on the turbulence at this stage, but just for you to get an idea, first of all, that this fluid flow around wings is chaotic. It's very chaotic. You can see a lot of stuff happening here. I want you also to focus on the fact that there is some coherent behavior. These are so-called coherent structures, and I'll be talking about them also in just a second. And also for you to realize that this has an application. This is about the aerodynamics and the physics around solid surfaces, airplane wings, vehicles, ships, all these areas where we can actually try to, in the end, maybe diminish the drag. No, we want to understand what's going on. We want to try to get ideas for better design later. Okay, so this is a highly resolved simulation. This was published in the Journal of Fluid Mechanics last year. All the data is available online, so you can just download and check all the databases and all the information that you may be interested in. Let me start also by talking about some motivation. So how can we control a turbulent flow? And by control, I mean to try to make the flow do whatever we want it to do. Like give us reduced drag. So if we take one of those regions, those structures that you saw before, some of these chaotic motions, what I would like to do, first of all, is to identify what are the most important regions of the domain. So if I have these chaotic motions that you see around the wing, which ones are important and which ones are not? So if I could find a way to find what's important, that would be helpful. Like, for example, these red regions over here. And then once I have identified what is important, if I could find a way to remove what's important, right, and then just leave aside the rest, then I might be in a position where I can actually be able to control the flow, where I can actually be able to achieve better performance because I'm removing the critical things in the flow that are sustaining that turbulence mechanism, the turbulent fluctuations in my flow. So I want to basically structure the talk around these two words, identify and remove. And that's going to be the two parts of my presentation. In the first part, I want to identify what are the most important regions with explainable deep learning. In the second part, I'm going to remove those regions by controlling the flow through deep reinforcement learning. Okay, makes sense so far? So we start with identifying the most important regions with explainable deep learning. So I want to highlight in red the important parts of my flow. So the question of what are the most important regions of the flow has been asked many times. It has good consequences and crucial consequences in terms of control and sensing. Encinar and Jimenez looked at this question from the perspective of being able to do perturbations from intrusive causality assessments. So they would basically add perturbations in the flow and then numerically resimulate the flow many times and try to analyze the perturbations that grow the most. And those would be basically characterizing the most important regions of the flow. So that's one way to do it in an intrusive manner. Lozano, Duran, and Arranz, they do this in a non-intrusive manner, so they don't need to resimulate the flow, and they use information theory and causality analysis. First of all, they need to have time series, and one way to get time series from the spatiotemporal data of the flow is through modal decomposition, PCA, for example, right? So you have time series, and then what they do is that they remove the information of one time series, and they see how that removal affects the prediction of the other time series in the future in such a way that one can systematically, using information theory, assess what is the relevance of each of those time series on the other predictions, basically. So these are two ways to study the question, what are the most important regions of the flow are and how we can characterize them. The way that we try to answer this question is a bit different. We develop a method that is intrusive on a surrogate model. So we're going to build a surrogate model, and that's going to be built with a deep learning method. And I'll tell you more about it in just a second. The advantage of our approach is basically twofold. First of all, it can be applied also to experiments. So you don't need to resimulate the flow all the time. And it can be applied to the whole flow field, not just the time series. Okay, so there's some advantages to using these deep learning methods. And we're going to start with a turbulent channel flow. So this is the flow between two plates. I'm not going to go to the wing. I'm going to have a simplified geometry of the same type of chaotic motion at a low Reynolds number. It's not going to be very, very chaotic, but it's going to be turbulent. And one first analysis that we're going to do is analyze this type of structure that you can see here, which is the so-called Q event. These are regions of a strong Reynolds shear stress, which are basically regions where the velocity in U and the velocity in V, so these two directions, they are highly correlated and they have a high value. Okay, so basically, this is something that Lozano, Duran, and others have looked at for many years, where they identify three-dimensional regions where this product, this velocity correlation, is actually very high. Okay? And this is, in a way, the classical view of what's important in the flow, the Reynolds stress. What we want to do with our method is develop this explainability algorithm. We start, and the method has three parts. First of all, we need to create that surrogate model such that given the current state of the flow, the fluctuations of the present step, I want to predict the fluctuations in a future step. Okay? So the flow field is advanced in time with a 3D UNet. This is basically a computer vision method based on convolutions, basically. So I can predict a future state of the flow. Second, I want to identify these Q events in my input, so these structures in my input. And third, what I want to do is use this game theoretic algorithm called SHAP, which is relying on Shapley explanations. And I guess many people here know about it. Essentially, with this Shapley framework, we take one of these structures from the input, we remove it, and then we repeat the prediction and see how the error has changed. We see what is the impact of each of those structures from the input on the future evolution of the system. Okay? And this was developed by Andres Cremades and others. He's a postdoc in my group and published in Nature Communications last year. All the code and all the data are available online. So you can just, at the end, you'll get a QR link, you can access everything, and you can ask any questions that you have. So all of this is open access. If we go a bit more into details in the UNet, this is a pretty standard model. So we just have our input, again, is three-dimensional fields of fluctuations in the U, V, and W fluctuations. So the three directions, the velocity fluctuations in the three directions, three-dimensional fields. The output is the three-dimensional fields, 5 viscous times into the future, although the results are pretty robust in a pretty broad range of time intervals. These are essentially time intervals characteristic of the region very close to the wall. And a UNet, as many of you know here, is relying on convolutions, where I basically start with my input field. I apply a number of convolutions. I do a max pull, so I reduce the resolution. I apply more convolutions, another max pulling, and this is the lowest resolution, then an inverse convolution here, another inverse convolution here to recover the original resolution. Now, convolutions are interesting in the context of turbulence because they can exploit the spatial patterns, and as you saw in the video, turbulence is highly concentrated in coherent regions of a lot of information. So those spatial patterns can be exploited by the convolutions in a pretty effective way. And a key feature of the UNet is this skip connection, this residual block, where I'm connecting feature maps from early in the network, where you have smaller and more abstract features, with feature maps late into the network, close to the output, where the features are larger and they're also more refined because you have applied many more convolutions. So that combination of early stage feature maps and late stage feature maps at the end really helps us a lot to improve the predictions. Okay, so this is to predict the flow field in 3D, which is just basically going to be a step in our SHAP framework, so our framework of explainability. So in a nutshell, what I have is my three-dimensional flow fields now in the present step. What I will do is apply the UNet to predict the future state of the flow after a few viscous units. And then I will compare my predicted flow fields with the ground truth, which is the DNS. This is the very highly resolved simulations, right? And I will calculate my error. And that error is typically less than 1%. So I get a pretty good prediction. Now what I do is that I remove one structure from the input. I run my UNet again, and I get a new prediction. And I will compare my predicted flow field when I have removed the structure with the ground truth and recalculate the error. And by looking at how the error is changing, when I remove this structure or that one, I can assess what is called an importance score. So each structure gets an importance score, which is basically the SHAP value, based on how much the removal affected the prediction of the future state of the flow. Okay? So that's the main idea of the SHAP values. There are some, a little bit of technical background on how we do it. In practice, to calculate the SHAP, we use this linear model G. This linear model is a linear model between the prediction of the neural network and the ground truth. Okay? And in this linear model, we have all these variables, Q1, Q2, Qn, which are binary variables which represent the presence or the absence of each of the structures in the flow field and in all the snapshots. So all the structures that we can consider in our simulation, basically. Now, another thing here that we have is that these phi values that you see here, which are basically weighting factors of each of those structures, these are basically the SHAP values. So how much each structure contributes to the model of the error, this weighting factor, this is the SHAP value. And the SHAP values are calculated by solving this least square problem, where I have f hat would be the real error between the neural network and the ground truth, and G, which is the linear model of that error. So when those two are minimized, and there is some coalition selection that is done through game theory here, when those two are minimized, then I basically obtain my phi values, my SHAP values, essentially. Okay, so I'm just trying to develop a linear model for the error, and I can get a pretty good assessment of the contribution of all the structures through this SHAP methodology. Okay, so there's some technicalities about this. If you have questions, we can discuss them at the end. Let me start with some of the results so that you can get an idea of how these SHAP values help us to understand what the flow is doing. In this first figure, what I'm showing you in the vertical axis is the absolute value of the SHAP score, so the importance as a function of the volume of the structures. Okay, this is a joint probability density function of all the structures. You can see that there is a pretty good correlation, right? So in general, larger structures have higher importance, which is something that intuitively kind of makes sense. The bigger volumes have higher importance. But if I express now in the vertical axis, I'm showing you the importance divided by the volume, so some measure of the specific importance as a function of the volume, then the picture changes, the correlation is gone. The largest things are in this blue balloon over here. They're not the most important anymore. The most important stuff is in this red balloon over here. These are the ones with the highest importance per unit volume, and they are essentially what we medium-sized ejections. So the ejection is a flow that is close to the wall that is going up and backwards. That's the type of structure with the highest specific importance in this analysis. Okay. Now, another question that we may ask ourselves is, sure, we're looking at three-dimensional regions of Reynolds shear stress, right? So if I plot the importance as a function of the Reynolds shear stress, this is the right panel, importance as a function of the Reynolds shear stress, we see another pretty good correlation. So, I mean, that's probably not so surprising. I am looking at regions of Reynolds shear stress, at the ones with the highest Reynolds shear stress are the ones that are most important. Also because they are the largest, right? So in principle, that's kind of a bit intuitive. But if I represent the importance per unit volume as a function of the Reynolds shear stress per unit volume, now things change a lot. So the correlation that we found before between the importance and the Reynolds shear stress is gone. You can see in this A region over here a bigger spread of importance values. In region B, you can see the structures with the highest Reynolds shear stress, and in region C, you can see the structures with the highest importance per unit volume. And to give you some context, in theory, in turbulence theory, it has been thought that these Reynolds stress structures, these Q events, are typically the most important, or at least very informative to understand what's going on in the flow for different physical reasons. But what you can see here is that perhaps that hypothesis was not completely true, because the most important things, which are in this C region, are not the ones with the highest Reynolds shear stress, which would be in this B region. So this already gives us some indication that the classical understanding, the classical intuition may not be always right when you look at things in a more objective manner. No? This is a first result. But of course, we want to also test this experimentally, right? I mean, I told you that we could do it with experimental data. This is something that we did together with Ivan Marusik's group in Melbourne, in the University of Melbourne, where the reason why I want to test this experimentally is twofold. The first one is, if I am doing a simulation, a very detailed simulation at a low Reynolds number, and remember the Reynolds number tells me how chaotic the flow is, and I see what is the most important structure there, perhaps when I do a simulation, an experiment at a high Reynolds number in a more chaotic condition, the most important stuff is not the same, right? So it may be important to analyze this assessment of importance in the experimental data. But second, even if I could do a simulation at a very, very high Reynolds number, perhaps the nicely resolved three-dimensional elements that you see in the computer, in the simulation, cannot be measured in the experiment, because in the experiment you usually have limited access with resolution, with probes. The best that you can do is have maybe two-dimensional planes, but not the whole three-dimensional nicely resolved data. So the question is not what is the most important structure in the flow. The question is, from whatever I can measure, what is the most important? Because if I want to apply flow control or I want to do something with my flow, I'm going to have to rely on experiments. So from the stuff that I can measure, what is the most important? That is my question. So we use this towing tank experiment by Ivan's group. This is a pretty cool experiment that you can see here, where you have a plate and the plate is set into motion, and then the flow grows in time. So instead of having a boundary growing in space, it grows in time. Okay? And we had a pretty similar database to the numerical one, with two differences. We have only 2D data, right? Because they can only measure the 2D plane. And the Reynolds number was an order of magnitude higher. So this is an order of magnitude more chaotic, if you want to think of it like that. So we want to test where the results change when the Reynolds number is higher, basically. And you can see that the results are actually pretty similar when I compare the experimental and the numerical output. The importance as a function of the surface, because now I'm looking at 2D data, so the structures are measured by the surface, they're still pretty well correlated. And the importance per unit surface as a function of the surface reflect the same three balloons as before. The largest structures are not the most important, and the most important things in this red balloon are, again, medium-sized ejections, right? So in principle, the experimental data reveals similar conclusions. If I look at the importance as a function of the Reynolds shear stress, again, pretty good correlation. And if I divide the importance per unit surface by the Reynolds shear stress per unit surface, I also find the same three regions as before, where critically, the stuff with the highest Reynolds shear stress is not the most important. This is the stuff with the highest importance, and you can see that over here, there is stuff with very high importance and very little Reynolds shear stress. So this also corroborates the initial conclusion that perhaps the classical view of what is important and what is not necessarily correct, right? When you look at things objectively, then things can be a bit different. Now, what I told you so far, or what I did so far, was a little bit biased, okay? It was biased because I was choosing what extractors I was analyzing from the beginning. I was looking at these 3D volumes of Reynolds stress, and I was telling you, okay, this is important, this is not, whatever, right? But ideally, what I would like to do is to look at each point individually and assess the importance of each point, to try to look at regions, at extractors, purely based on importance. That's something that we did with experimental data by Ivan Marusik. So instead of, we use a different variant of the SHAP method called the gradient SHAP, which is more computationally efficient. This can be applied to each grid point. So instead of having to apply the importance to one volume, we just do it to each grid point of my domain. And the gradient SHAP gives me one importance score for each of the velocity components. At the end of the day, I can just create a norm and look at regions of high importance by using percolation analysis. Okay, so I basically compare the instantaneous importance with the average importance over the data set, and then I can look at regions of high importance with respect to the background importance levels. What I'm showing you here in black is the Reynolds stress extractors, the classical ones, and in green, I'm showing you these extractors based purely on importance. So remember, I'm applying this SHAP analysis point by point, and I'm just clustering the regions of highest importance to create new extractors. And what we see is that there's about 70% overlap, which is in principle good because it tells me that the classical extractors, they're not so wrong. I mean, at the end of the day, regions of high fluctuation need to be important, but they don't tell me the whole story, right? There's 30% missing that is kind of only understood when we look at things more objectively with the SHAP method. So what we did, and this is up to the point that we published last year in Nature Communications. So now what we wanted to do was to extend this with numerical data. So we wanted to do the SHAP analysis point by point from the DNS, from the highly resolved numerical data. We took a much bigger computational domain, and then we applied the SHAP analysis point by point. So remember, I take 1 point, I repeat the prediction, I take out 1 point, I repeat the prediction, and I group the regions of highest importance for each of the instantaneous realizations of my flow, okay? And you can find the preprint for this in arXiv. So this is an extension of the previous work. Here I'm showing you instantaneous snapshots of different types of classically studied extractors. So in the top left corner, our extractors based purely on importance. Remember the video that I showed you at the beginning, right? That you were seeing all these chaotic things. Well, this is what these chaotic things would look like if I define them purely based on importance. On the top right, I'm showing you the Q events, the classical ones that I was talking about before, the ones based on this Reynolds stress. So this is a type of extractor that is based on classical knowledge. Bottom left, the streaks. This is another type of important extractor which has been studied close to the wall. And vortices, which is what I showed you in the video. By the way, when people do simulations of fluids, of fluid mechanics, they do CFD, which is computational fluid dynamics, but also sometimes colors for directors, depending on how you want to look at it. What people usually show is these vortices, right? So basically regions of high rotation. What we want to do now is from the classical extractors, which are the most important. I mean, how do they compare the classical analysis with our analysis that remember, the only thing that we do is that we take away each point. We see if it's important or if it's not. We group and cluster the groups of highest importance. Then we get these guys over here, these elements over here. And what I'm showing you in this figure is the joint PDF, the joint probability density function of each of the extractors, right? So in big, I'm showing you the SHAP the ones that we define based on importance. In the vertical axis, I'm showing you the distance from the wall, and the horizontal axis, I'm showing you the streamwise velocity fluctuation. Okay, so for each of the structures, for the whole database, we do a statistical analysis so we understand basically where these structures are in this probabilistic map, right? So what are their velocities and what are their locations? Okay, and I compare this joint PDF with the joint PDFs of the Reynolds-stress events, the ones that I was talking about at the beginning, the streaks and the vortices. And if we compare these maps, we see some interesting trends. We actually see that here, this region over here of the SHAP PDF is very similar to this one. This is what we call sweeps, so flow going close to the wall. Over here, this region is very similar to this one, and this is what we call ejections, the ones that I mentioned before that are going farther away from the wall. But if we look at more regions, this part is very similar to this one. This is a low-speed streak, and this part is very similar to that one. That's a high-speed streak. And even more, this region over here is actually very similar to this region of the vortices. So what you start to see now, by analyzing the probabilistic distribution of the characteristics of these structures, is that our structures, which are, again, purely based on importance, agree with the classical ones in different regions, right? But they're not exactly identical, but in different regions, they have different degrees of similarity. So our next natural step was to take the one-to-one agreement between the different structures. So we take, for one flow field, the SHAP, and we take the Q events, and we see the percentage of agreement for that flow field, and we average that for the whole database. The one-to-one agreement between the SHAP and the vortices, and the one-to-one agreement between the SHAP and the streaks. And we find something actually pretty interesting. This blue line over here, and in the vertical axis, I'm showing you the agreement between structures. In the horizontal axis, I'm showing you the distance from the wall. This blue line over here shows the agreement between the streaks and the SHAP. And you can see around 90% agreement in this region, where the streaks are very pronounced. This is where the streaks live, and about 0% agreement everywhere else, right? It goes down very quickly. The Q events, the Reynolds-stress structures, the classically static ones, they have about 60–70% agreement close to the wall. These are the sweeps, and far away from the wall, these are the ejections. Also about 60–70% agreement. And the vortices, the ones that people show in the videos, like the one that I showed you before of the wing, they only have about 25% agreement with our structures and in one particular region of the domain. So two things become clear. First one is that the classically studied structures in turbulence only paint a partial picture, right? None of them really reflects the trends of our importance-based structures. Ours are based purely on what is important and what is not. And the classical ones only agree partially in different regions. And the second one is that the vortices, which is what people visualize quite often, they have quite low importance. So they are really not something that is super relevant to the temporal evolution of our flow, basically. Okay? So this is an important message of how we can use explainable deep learning, data-driven methods to try to understand the intricate physics of all these complex phenomena. This first part was about identifying what is important and what is not. And the second part has to do with control. So once I identify what is important, I want to remove it. Because if I remove what is important, I may have a good chance of being able to reduce the drag, right? I mean, turbulence, in some cases, it can be good because it enhances mixing. In the cases of the flow on a wing, for example, it's typically bad because it increases the drag. So if I identify what is important for turbulence and I find a way to remove it, then I might be able to reduce the turbulence and reduce the drag. Okay? So to remove what is important, I'm going to use deep reinforcement learning. Okay? And it is a very short recap of deep reinforcement learning. I understand that many people in the room know about this method. We have some work with Luca Guastoni, and this paper, Vignon and others in physics of fluids, this is a pretty complete review paper of reinforcement learning for flow control. So if you want to learn more about how we use this method for fluid mechanics, this is going to be a good paper. And Luca Guastoni, who was a student in my group, he's now a postdoc in Munich, he did a lot of the work that helped us to develop these things for the channel, for turbulent channels. So what happens in reinforcement learning? Well, we have an agent. This is typically a neural network. And the agent interacts with an environment. And the environment is going to be our flow. And in our case, we do this numerically. This is our simulation, but you can do this experimentally as well. The important thing is these arrows. There needs to be a closed loop between the agent and the environment. The agent needs to be able to interact with the flow. And the agent interacts with the flow through actions. And that action is what we call flow control. Okay? So that flow control, in our case, is going to be jets on the wing surface where we do blowing or suction. Okay? So we do those actions. And the environment is going to be affected by those actions through changing its state. So the flow field is going to change. The typology of the flow is going to be modified, and by providing a reward. And the reward is a measure of the quality of those actions under a certain norm. So in my case, if I want to reduce the drag, the reward is going to be the drag reduction, for example. So the agent is going to be iteratively trying different things on the environment and seeing how the reward changes, and through the reinforcement learning algorithm. And there's different algorithms, DDPG, PPO, depends on what you want to do. But typically the idea is to optimize a policy pi, which given the state of the system, given the flow that you have, it decides which actions to take to maximize the reward. Okay? So what I want to do is find that mapping, from the state to the action to maximize the reward. So the flow that we are going to consider is also a channel. So again, in this case, we're actually going to consider a channel that is open. So we have a wall at the bottom, and at the top, I have a symmetry condition, basically a wall-bounded flow. And we're going to consider both a minimal channel, where the physics is actually a bit simpler, and a full channel where the physics is basically a complete turbulent flow simulation at a friction Reynolds number of 180, which is not very high, but it's turbulent. So we have a turbulent flow here. Okay. Again, this is the work by Luca Bostani. So this is the case that we're going to look at. And our baseline, our benchmark to see if our control is doing well or not, is going to be a classical control, which we call opposition control. In opposition control, what we do is that we are going to be, if we have the wall here, we're going to sense the flow above in the region where the streaks are maximum, so this distance that I showed you before, and we're going to measure the vertical velocity. So if the flow is going up at this location, at the wall, we're going to do the opposite. We're going to go down. And if the flow is going down up here, at the wall, we're going to go up in such a way, in a bit of a simplistic way, to try to oppose those fluctuations, to try to cancel those fluctuations. Okay, this is a pretty simple model of control, trying to see if I do the opposite, maybe I can get to reduce the turbulent fluctuations. And that's the classical approach, the opposition control. What we're going to be doing with the reinforcement learning is a framework which is called multi-agent reinforcement learning. And I talked about this with several students before. I think you are probably interested. So this is the slide that you want to pay attention to. We also have a description of this together with Steve Branton and Beverly McKeon in Nature Reviews Physics about experimental implementations of this method. In a nutshell, we have the following. This region here, this is a region where the flow is homogeneous in both the stringwise and spanwise directions, because the flow is periodic. So we take advantage of the invariances in my flow. That means that statistically, in each of these small regions, which are called pseudo environments, the flow is doing statistically the same. But instantaneously, we are observing different things, right? Because the flow is chaotic. In each of these pseudo environments, we have the same agent. We have the same parameters of the neural network. And what we are doing is basically copy the same agent in all these pseudo environments such that I can speed up the training, because that way the agent is exposed to many more realizations of the same flow, basically, such that we can hopefully have a faster way of training. Not only that, when by the way, the state is going to be the fluctuations, the U and V fluctuations above the this state, the agent needs to decide the action, which is going to be the velocity at the wall. So remember, we are going to have jets at the wall that can either blow or suck. So in each of these pseudo environments, I will have one or more actuators that are going to be blowing or sucking, depending on what the reinforcement learning agent is deciding. Is that the reward is going to be the drag reduction. In this particular case, wall shear stress reduction on the whole wall, you can also define this as a local reward with some partial overlap with neighboring pseudo environments. The idea is that because all the agents are the same, Right? This is in all the studio environments, I have the same parameters, and the reward is somewhat global. All these agents start to cooperate to achieve the highest possible drag reduction. So instead of having each studio environment fighting its own war, all of them try to really achieve the highest drag reduction. Okay, so that's a way where we can try to beat the curse of dimensionality. Yes.
Can you have instances where you have individuals who still get information, or would that be nonsense?
So we have an example. I think the video that I showed this morning, you saw it with the relevant convection of the single agent. So that would be the other extreme, where each of them is doing their own work, basically, and that works much worse. You could do something in between. However, I think that based on how turbulence works and the high dimensionality of the system, I mean, this multi-agent really helps us to scale up the training in these turbulent environments. So I think this is probably going to be the better alternative. Okay, so this is the method. Let's look at some results. When I do the training in the minimal channel, remember that in the minimal channel, the physics is simplified. The opposition control, that's the baseline, that's the classical method, gives me 26% drag reduction. This is the orange line. The reinforcement learning really beats it, and we get 43% drag reduction. Okay, so with a reinforcement learning algorithm, I can discover a much more sophisticated control than just simply opposing the flow, right? I do something a bit more interesting. And that means that I can effectively tackle the near wall dynamics of those streaks. In fact, if you visualize the flow, what you see is that the streaks, those structures close to the wall, are there, but they are completely stabilized. So there's no meandering or no instabilities in those streaks. If I use the agent that I train in the minimal channel and I deploy that in the full channel and I run it in a deterministic manner, what I get is 20% drag reduction from the opposition control, the classical method, and 30% reinforcement learning. So there is a clear difference. We really get a much better performance when achieving or deploying this control in the turbulent flow. Okay, so reinforcement learning can discover more sophisticated control strategies through this capability of being able to explore by trial and error many different configurations. In fact, if we look at the control, what the control is actually doing, this is a joint PDF where in the horizontal axis, I'm showing you the stringwise fluctuations, stringwise flow. In the vertical axis, the wall normal fluctuations, the vertical flow at y plus 15. That's the plane where you have the streaks. So that's an important plane. And if you look at the no control case, which is at the top, what you typically do is divide this into 4 quadrants. So you have 1, 2, 3, and 4. And what you expect in turbulence is that the top left and the bottom right panels, so this diagonal, is dominant. Okay? The top left are the ejections, the bottom right are the sweeps. So that diagonal is typically dominant. And this is, by the way, what we saw also with explainable deep learning analysis of before. Right? So everything is kind of consistent. When I do opposition control, what happens is that I have the same distribution, but it gets a bit shrunk because obviously the opposition control is reducing the range of the fluctuations, but you can see that the dominance of the top left and bottom right panels, so this diagonal, the flow hasn't really changed so much. The flow is doing something pretty similar. Okay, so fundamentally, I haven't really affected so much the flow. In the bottom panel, I'm showing you the results from the deep reinforcement learning. And what is interesting now is that the predominance of the top left and bottom right panels is gone. And you get a pretty even distribution of the fluctuations across the 4 quadrants. Once again, meaning that I have a pretty fundamental and deep change in the characteristics of the turbulent flow. So the reinforcement learning is really finding a completely new way to control the flow. What is the reinforcement learning doing? Well, if we look at the bottom... Yep.
So it seems that with DRL, you decrease VRMS.
I decrease VRMS. Yeah, I decrease the VRMS. Yeah, I decrease VRMS, exactly. And what happens is that the streaks are still there, but all the meandering that is connected with the V, of course, with all the lift-up mechanism, that's kind of stopped. So they're kind of very stabilized, the streaks there. And we're going to visualize what the control is actually doing. The opposition control, it starts quite high, and as the flow gets controlled and the drag is reduced, the magnitude of the fluctuations gets smaller, and of course, I'm just opposing those fluctuations, right? So I'm just following the magnitude of the fluctuations as I evolve in the stringwise direction, in time. But what the reinforcement learning does, which is this blue line over here, I have a cap from minus u tau to plus u tau. So these are the limits of the control. What it does is a two-step control. It's a bang-bang control. So it's really trying to stabilize the streaks by blowing as much as possible and sucking as much as possible with frequencies that are not predetermined because the system is chaotic in the end, but it's finding a type of bang-bang control, which, by the way, it's really found in many contexts, like in robotics, in drone control, bang commonly found by reinforcement learning applications. So this is quite similar to previous works of reinforcement learning applied to engineering applications. Now, we have seen how we can control the flow with reinforcement learning by trying to minimize the drag. So I put in my reward minimization of the drag. But in the first part of the presentation, I showed you that we can understand and identify what is the most important part of the flow. Right? We really identify those sharp structures based purely on importance. So what if in my reward of the reinforcement learning, what I do is not reduce the drag, but reduce the important structures on the flow, reduce the sharp. And I'm going to compare this work by Miguel Benitez, by the way, who's a postdoc in my group. The reinforcement learning setup is very similar. The only thing that changes is the reward. So I'm going to compare a total of 5 cases. First case is the opposition control, right? So same as before. Second case is the reinforcement learning where I want to reduce the wall shear stress, same as before, right? So the reward is to minimize the shear stress. And I am adding 3 different cases now. Another case where the reward is to minimize the Q events, so the Reynolds stresses. Another case where I want to minimize the streaks, so the other classical structure. And finally, in purple, this color code is going to be maintained in the next slides. In purple, the reward is to minimize the sharp. So I'm going to tell the reinforcement learning to find new ways through blowing and suction to minimize the important structures in the flow. Okay? Conceptually, this could make sense as a way to minimize the drag, because I'm not just saying to reduce the drag, I'm just saying, look, identify what is important. So don't go after the drag, go after the guys that are the important ones. And let's see what happens. What I'm showing you here at the top is the drag reduction as a function of time. And I'm showing you different lines. The purple one with the arrow, this purple one is the one where I'm using as a reward the sharp, the most important structures. You can see that this is the case with the highest drag reduction. Then in orange, I'm showing you the case where the reward is the wall shear stress. Okay, so the one that I showed you before. And that's a bit below. I mean, you can also see that the drag reduction as a reward is less stable than the sharp. So in the sharp, the variability is actually very small. In the case of the wall shear stress, we have a much larger variability. In green, we see the reduction of the Q events, which has less drag reduction. In fact, interestingly, when I try to reduce the streaks, I get the worst case, even worse than the baseline, which was the opposition control. So if you compare cases, the reduction of, so when the reward of the reinforcement learning is the wall shear stress reduction, I get 31.7% reduction. When I use the sharp, I get 33%, 0.3% drag reduction. With a more stable than just doing the reinforcement learning, and 5% better drag reduction than just targeting the wall shear stress reduction. Which, you mean those variations, that comes from the, I mean, it's a chaotic system that you're trying to control. So it comes from the reaction of the flow to the actions that I'm putting on the system. Right. Well, it has to do with how often you update the actions also. So we are updating actions more or less in those intervals. So it probably has to do with some of the variability of how you update your policy. And by the way, the physics of how we update our control have to do. So we update a policy about few viscous units. So basically a few characteristic times of the smallest structures of the flow, basically. So it's associated with how we are updating the control. And this is the cases with the highest performance that we got. This is purely drag reduction, but of course the control has a cost because I'm injecting flow and I'm also, sucking flow. Then the metric that is going to be interesting is what we call the net energy saving. In the net energy saving, we have the skin friction reduction, basically, I reduce to get the actual skin friction from the control flow by to take into account the power of the control. And the power of the control is this term over here, which is basically 1/2 times the velocity at the wall cubed. So that really measures how much flow we're pumping or sucking from the flow. Interestingly, what you can see in orange, we got the power from the all reinforcement learning, where the reward was the wall shear stress reduction. In purple, the power from the control, where I'm controlling the most important structures in the flow. You can see that the cost of the control is half. So not only I get more drag reduction and I get a more stable control, I also use half of the energy to implement that control. So in terms of the net energy saving, I'm 5.4% better than just doing drag reduction with the reinforcement learning, basically. Okay. Now this I believe this is a pretty interesting result because it really shows that with purely data-driven methods, I can first look at what is the most important part of my flow. I can find a data-driven method to control that, which is the most important part of the flow, and that gives me the highest drag reduction of all these methods.
That we half the power.
Yeah.
Does that mean that we pose weaker wall normal fluctuations?
Yeah, exactly. So this is 1/2 times the velocity of the wall cubed. So that's the modulus of the power that is being pumped. This is half of it. Yeah. I also, before finishing, I also wanted to illustrate other examples where you were using, so we're really being able to scale up reinforcement learning to control turbulent flows at much higher Reynolds numbers. This is some work that we just published in Nature Communications, where we are controlling a turbulent separation bubble. So to reduce separation, reinforcement learning really beats classical periodic control, and this is at 8,750, so this is a higher Reynolds number case. We also have control in 2- and 3-dimensional cylinders. So as I increase the Reynolds number and the wake gets much more chaotic and 3-dimensional, the reinforcement learning adapts to the new scales that basically arise in the span-wise direction. This is work by Paul Suarez, who is a PhD student in my group. And this is relaminar convection in 3D. This is published in Flow, Turbulence, and Combustion, where Joel Vassant, who was a postdoc in my group, really found that the convection cells in the 3D relaminar convection really get completely realigned in these diagonal patterns with reinforcement learning in such a way that we can minimize quite significantly the Nusselt number. So we minimize the heat transfer from the bottom to the top wall in 3D settings, also with the capabilities of these reinforcement learning algorithms, always leveraging the multi-agent reinforcement learning framework. Okay? And these are my conclusions. I showed that the SHAP method can be used to identify the most important regions in a turbulent flow, which is a quite daunting task because turbulence is very chaotic, but we managed to find the most important things. Second, with reinforcement learning, we can achieve higher drag reduction than with opposition control. And third, if in the reward of the reinforcement learning, we put the minimizing the most important stuff in the flow, then we get simply the highest possible drag reduction of all the cases that we looked at. Okay? All the codes and all the data are available online. So please feel free to use this QR code to access the repository of my group. You can also see a lot of these things in my YouTube channel. So I have a lot of videos explaining the different methods, the different papers, and also in social media, you can reach out to me. That's all I have for today. I'll be happy to take your questions.
So, yeah, very impressive work, especially towards the control in the end. So how practical, so this is all sort of simulation based, so how actionable is this, for instance, for practical design?
Yeah. That's a very good question. So we're actually implementing this in the wind tunnel. So we have several projects where we are actually putting this in the experiment. If we think of the case, so basically the case where we are doing the drag reduction for the wall shear stress, so the reward is the wall shear stress, that's the simplest to start. There are some challenges because you need to be able to measure the flow, to get the state, send the state to a computer or a car to do the calculations external, evaluate the reinforcement learning, calculate the action, and send it back in time to control the structures, right? For the larger scales, this is pretty straightforward. I mean, we did some estimations. All of this evaluation takes on the order of milliseconds. And the scales that we want to control are not super high Reynolds numbers, but at this range of Reynolds numbers is on the order of 20, 50 milliseconds. So we are basically an order of magnitude faster than the scales that we want to control. But of course, and we are now designing and getting the actuators and getting all the loop. So there is some work to do, but in principle it's feasible. And we are also working on the case where we will actually minimize so not only minimizing the World Series stress, but also minimizing the SAP. So short answer, we are working on it and it looks feasible.
So you were using this SHAP analysis to identify these sort of common modes. So I'm not sure, it's probably very familiar for you and probably a stupid question, but also dynamic mode decomposition, right, to identify coherent flows, coherent structures in flow. So the SHAP analysis, I would imagine that looking at the leading singular components of
So that's a very good question. What one does with dynamic mode decomposition or POD or PCA, that's something called feature extraction, right? Because you go to a different basis. That's what you would get with autoencoders also, right? And then the modes that you find are not physically on the flow. They're representations in a different basis. And if you superimpose all those modes that you get, then you reconstruct the flow, right? But the POD mode does not exist. It's a representation on a different basis. That's why it's called feature extraction, right? What we do with SHAP is feature selection. So we identify extractors from the stuff that is happening instantaneously on the flow, right? So of course, there's physical connections between a POD mode and a SAP extractor or a streak or things like that. But the main difference is that when you do model decomposition and when you do a feature extraction, these things don't exist instantaneously on the flow. When you do SAP analysis, these things exist instantaneously on the flow. You can see their characteristics, you can measure their sizes. And when I control, I prefer to control things that exist instantaneously on the flow. I prefer to control this feature selection rather than feature extraction. This is what it looks like instantaneously, right? A POD mode is kind of like an average leading order representation of this, but it doesn't exist in the flow instantaneously.
So represent each point that flow as in that basis, right? And then use that as a basis for control.
That's correct. But when I need to control, when I do reinforcement element to control SHAP, what I say is, if you find this, control that, minimize this stuff. But in the case of the POD, of course, having said that, POD or DMD gives you useful information. I mean, even if that stuff doesn't exist instantaneously on the flow, you may get the frequencies, right? And and then I'm like, okay, I don't find the POD mode here, but I know that the frequency is, 2.5. So if I blow or suck with 2.5 hertz of frequency, then I might do something to the flow, right? Yeah. But my idea is to go one step beyond that and see, no, I want to see exactly what's happening on the flow and control that. And that's what you can do with the SHAP.
What part did you work on volume?
Sorry, can you repeat?
What part the average over volume?
Yeah.
Why not point by point? Didn't understand that.
At the beginning, you mean when I do
How big the exhaust, whatever it was, what per unit volume or over the volume? Why not at each point, as you always do?
We also did it point by point. Because I wanted to, so I mean, we're comparing, for example, this and this, right? So this is the importance and this is the importance, right? Yeah, so I mean, this is, the classical expected analysis, no? Larger things are most important, but I wanted to look at the specific importance because that's maybe telling me different information, right? I mean, there might be something that is smaller, and in this figure, maybe it's in the middle, but it's very small. So if I want to control that, I mean, maybe it's going to be easier to control something very small with very high importance rather than something very big with high importance.
Double the resolution, this figure will change.
Well, this is DNS. So this is already, yeah, I have all the extractors. Yeah. Yeah. Well, when I control, let me go to the slide of control so things are a bit clearer. Yeah. I mean, the point by point would be basically I mean, this analysis, no, the sharp defined point by point, or this one.
You're trying to see if you change the vector in one point of the flow, how much it affects the final prediction.
Yeah. So that's from a methodological point of view, how SHAP is done, right? So SHAP, when I do it point by point, well, I have a unit that allows me to predict the future state of the flow. And then what I do is, okay, this pixel, I remove it. I repeat the prediction and I see what the error looks like. And I assign it an importance score. If the error changes a lot, that means that this is a very important point. If it doesn't change anything, that means that it's not an important point. That's a very good question. So this is something that I didn't show because it's a bit of the details, but in reality, this is not just on point by point, but it's on something called coalitions. So you take groups of extractors. You take groups of extractors and you do this analysis for groups of extractors. And then one single extractor or point. No, let's talk about points now. So the role of one particular point is not assessed only once, but it's assessed in many of these coalitions where you can really see its role in different contexts. When you have a lot of near wall information, a lot of outer flow information, and the final importance score is a weighted average of all those contributions. So the interscale contributions, which I agree are important, they are taken care of by this coalition analysis. I think I have a slide here. Yeah, this is basically the coalition analysis that we do. And this is the game theoretic part. If you remember, there was one pi x, one kernel that I didn't discuss too much. All this coalition analysis is in that kernel. Yeah. Yeah. Yeah.
How would you decide like that threshold in the error to decide SHAP score?
Well, no, there's not a threshold. It's just it's just contribution to the error. So the SHAP equation is a linear model. So basically, depending on how much the error changes, you get more or less SHAP. It's a weighting factor for this linear model of the error. So the SHAP, if I go back to the corresponding equation, which was here a bit at the beginning, but I think we can get there quite quickly. It's basically, so it's not binary. It's a real number. The SHAP value is a real number. So you get this. So for the total error, right, each of the features has a weighting factor, and the weighting factor is the SHAP. So basically, if the error changes very little, this will be very small because there will be no contribution to the error. And if the error changes a lot, right, then obviously this term will be high in this linear superposition of terms. Therefore, this phi value will be high. Make sense?
Great. I think for sake of time, maybe we can wrap up the questions there, but we have a pickup also outside with some pastries. So can stick around and ask also more questions to Ricardo and also have something to eat. So let's thank again the speaker.
Thank you so much.